Got it.
All right, today we're going to start talking about qualitative interpretation of position, velocity, time graphs, how they may be related, being able to pull information off them numerically, quantitatively, right, is where we'll end up. But a lot of what we need to know how to do is look at a graph and be able to determine what, in general, is it telling us about what's going on with the motion involved. Right, so we're going to look at a couple examples today of an object moving, obviously with some sensors and stuff that are going to measure and automatically graph rather than us having to graph by hand how that's going to play or what that motion is going to look like. We're going to sort of then begin to discuss how objects can move and what those graphs look like so we can have a point of discussion and talk about it. If I see a graph, I should be able to tell how the object moved to make that graph or what's going on in that graph. So initially, we're going to have an object that's going to be launched across this track there. And I'm going to look at the position time graph. I want you to think about and predict what that position time graph will look like. So we have three choices, A, B, and C. Or D, none of those. So based on the little bit that we've talked about with position time graphs so far, make a real quick prediction. Write it down, talk to your neighbor about A, B, or C. When I launch this cart down the track, will the motion down the track graph look like? This one, A, B, or C?
I feel like because it's definitely not it's definitely not but I just feel like it's C because from the beginning and it's not going.
All right, initially, anybody for graph A? Anybody for graph B? Graph C? And anybody think none of the above? Some nones. All right, let's look at where by graph C, people. Why do you think it's going to be graph C, or what is graph C telling you?
Because there's no slope or angle of the line.
But if the graph looks like this, what's this graph saying?
It's constant.
It's constant what? Position, right? Which means, is it moving or not moving? Right? Graph C is constant position, meaning it's not moving. So probably not going to be the case. Where were any A's out there? All right. What does this graph tell me is going to happen?
Pick up speed.
It's going to, once it starts, it's going to then all of a sudden pick up speed? That's what you're saying. And then I have my graph B's. Why do you say graph B?
Oh, because it's going to be constant speed throughout.
A constant speed, which means for every second it should go the same distance that it went the second before. Does everybody agree with that? So we're down to one of these two. We have some none of the aboves. What do we think it should look like?
Well, it would start off pretty fast, but then would lose speed over time. So
Why?
Friction.
All right, if I told you this was a frictionless or virtually frictionless system, would you still have that opinion?
I know.
This is a virtually frictionless system. So now where do you think you're going to be, A or B?
B.
All right, so real quick, I will hold this pen. Hopefully, watch that move. And then it's actually going to come back. Stop there. Now, if I look at All right. So now if we look at this whole track of the motion, what does this point represent? At the top, about 3.5 seconds. When it hit there, right? So looking at the time before, roughly 3.5 seconds, what does my graph look like?
Like B.
Graph B, right? Does that make sense? Once the spring unloads, it continues to go right until it collides there. Right? Is everybody good with that? Now, if my change of position is constant, what is the ratio of change in position over time called? Sorry. Velocity, right? Or speed. Or speed if I'm only going in one dimension. So if we look at this graph or that graph, is there a way I can determine how much distance it changed over a certain amount of time?
Yes.
And what would that quantity be? Slope of this, right? Everybody good there? So if I look for about, I don't know, 3.4 seconds for it, or I'm sorry, at 3.4 it's at about 1.9, 1.7. And let's say at point 6 it's at 0.3. And my time, 0.6 seconds to up here was 3.4. Can anybody do that math for me real quick? 1.4 divided by 2.8 looks to be like 0.5 meters per second. Is everybody good with that?
Yeah.
Turns out that this little computer program will actually automatically graph that velocity for me. And if I look at it, what value does that appear to be? About 0.5, right? Halfway between 0.4, so it's 0.6. So this velocity equates to this slope. Does that make sense? If it had graph like this, I'm not changing position. What's the slope of that line?
0.
And if I'm not changing position, do I have any velocity?
No.
Now, what is change in velocity over time? Acceleration, right? Now, in this case, my velocity is, what do we call that?
Constant.
Constant. So if I have constant velocity, what should my acceleration be?
0.
0. Make sense? And what is the slope of this horizontal line? So slope of that velocity curve should give me the acceleration. And is my acceleration basically 0? All the way across? What happened right here? Change directions. Went from moving in the positive direction to changing direction in the negative sense, right? Went from going positively to going negative. But basically, that slope being equal to 0. Does that make sense? And we end up then with the idea that the slope of x versus t gives me velocity. The slope of velocity versus time gives me acceleration. All the time. The slope of position time will give me velocity. The slope of velocity time will give me acceleration. Now for us, it's going to be relatively easy, right? Because we're going to have usually linear type relationships that are pretty easy to find the slope of. Right? So the line's pretty straightforward. If we looked at the the situation we dealt with in lab the last couple days. Now, if I adjust the scale, now, that situation is very similar to what you looked at in lab, right? You have your card, you let it fall, right? You recorded a bunch of different times and came up with those position times to graph, but you ended up with, we talked yesterday about that being a parabolic graph, right? The higher the angle, what should happen to my parabola?
Steeper.
It should get steeper, right? Now, it turns out that if I take the tangent line to that curve at each of those points, I will get this graph. To do that here, though, mathematically, almost impossible to do it by hand. We'd have to know the function, right, the ax squared plus bx plus c, that parabola was, and we can take what's called the derivative of it, those of us who are in calculus, and we can end up with this graph of slope. Then we were able to take this information, x versus t squared, and find our acceleration, right? Which we could then plot. There's another way we could do that as well, which we'll talk about using position time and using a different equation that looks like this without having to do that mathematical derivative of that. Is everybody good there? Now, so that gives us kind of an overview of how those three graphs are related, position, velocity, acceleration, how those three quantities are related, how they're related graphically to each other. Then, like I said, the next part, or the biggest part of where we start that is, how can we look at a graph and figure out what the motion of that object looks like, or describe the motion of that object. So I've got a couple examples I'll throw up here on the board and you can look at on this paper. And we'll talk about using those graphs, right, initially of position time and then velocity time, to figure out what the motion looks like. There you go.
Are there only three? Yeah.
Does everybody have one?
Yeah, there's not.
Let's look at graph A, where we have a position time graph that looks like that. Right now, when we talk about one-dimensional motion, we're going to have some point fixed in space we call the origin. We'll let it be right here. Right? From here, what's my positive direction? On this thing, it's that way, but normally, where would positive be if I was looking at a number line? Right, and that's generally by convention the way things work. Right, like everybody else in the world is going to say right's positive, left is negative because a number line's built that way. I could say it the other way. Hey, left's going to be positive for me. That's fine. But when we talk about a standard graph you're given, it's going to be oriented so that right is positive, left is negative. Okay? So if we looked at this object, where would it start its motion? At the origin. In which direction is it moving? Which is right or left?
Right.
So it's moving to the right. Is it moving to the right at a constant rate or some non-constant rate? Constant. All right. What if I had a graph that looked like this for x versus t? Starting where? Moving which way?
Right.
To the right at a non-constant, or accelerating. Right? Accelerating. All right, what's the next one on there says? What does it look like? B has position time where I start here and go that way, right? So where is the object initially? To the right of the origin, somewhere. Which direction is it moving? To the left. And where does it stop? At the origin, right? At 0, where position equals 0. Does it move constantly?
Yeah.
All right, so go ahead and look then at C and D real quick on your own. So on graph C, where does my object start? Where away from the origin? Left or right?
Left.
Right, so on the negative side, so left. And which direction is it moving? To the left, right? More negative. Does that make sense? What about in D? It's starting where?
Left.
And moving where? Moving to the origin and stopping, right? Or the origin and stopping. Down below there, you'll see a couple of velocity time graphs that are pretty straightforward. One of them looks like that. Velocity time graph A. And velocity time graph B. Looks like that. On the first one, which direction is the object moving? To the right. Constant rate or changing rate? So we call that constant velocity. To the right. What about in B?
Constant rate to the left.
Constant velocity to the left, correct? All right. What happens if the object starts with a positive velocity but slows down and turns around? For example, there. Starts with a positive velocity, slows down, turns around. Let's try and draw that graph. That's part C. Think about where it starts as being my origin. And which way is it moving when it starts? To the right. And is it getting faster or slower? continues to get slower until what happens?
It reaches 0.
And then once it reaches 0, what does it do?
Goes down.
Begins moving in the negative direction and going faster, right? Does that make sense? It starts off at some speed, slows down until it hits 0, then continues to move backwards, or starts to move backwards in an ever-increasing fashion. Right? Take a look at that one real quick. See if we can get it to come out. So we're just going to look at velocity time here. I'll expand that. Starts at some initial speed. So it's pretty good there. Now on the back side of that sheet, you'll see some examples of stuff that's going on a ramp. All right? Origin placed at different places, the object moving up the ramp, down the ramp, whatever. And you're supposed to look at and try to figure out and produce velocity, position time graph, velocity time graph, acceleration time graph for each of those 3 cases. All right? And we'll talk about those then tomorrow. So.
For velocity,
Yep.
why doesn't it go back up like a? Like why does it keep going straight
it's
down?
increasing
Yeah, but
in the negative direction, right? It's
good.
getting faster going back, going in the negative direction.
when it goes up, it's going away from the origin. Right?
Right, but so it's slowing down, right?
Yeah.
The velocity is getting less and less and less in the positive
So
direction.
when it starts going back, why doesn't it go back up?
Because it's not,
going
because that would
towards-
be in the positive direction, right? Velocity is not speed, not how many meters per second is it going.
Yeah.
Also, what direction is it going,
Yeah.
right? So because here it's as far positive it's going to get. Now when it starts going that way, it's going in the negative direction,
Gotcha.
but slowly getting faster, more meters per second, but in the negative direction.
Okay.
Okay? Anybody else have a question? That's it.